Hello everyone, welcome to my lecture series on computational mathematics, which is very much interesting for the purpose of computing uh, and etc. Now we are continuing on optimization theory. This is part 2, and today we will discuss on finding extrema. There are some methods of finding extrema. Today we will discuss on analytical method for finding the extrema, mainly local extrema. Now we will go through some theorems and some series and etc. for finding the extrema. So it can be treated as a prerequisite of the hardcore optimization theory. This is actually the base. Actually, for optimization we are finding the best value of all possible values, all possible solutions in the feasible region or solution region. Now let us continue with the first theorem of finding the extrema by analytical method. The theorem is, let f be a function from I to r be a differentiable on the interval I, then f is increasing on I if and only if the first order derivative is greater than equals 0 for all x belongs to the interval I, and conversely f is decreasing on the interval I if and only if the first order derivative is less than equals 0 for all x belongs to I. We will discuss it. Now the first order derivative test for guessing the extrema or finding the local extrema and relative extrema. Now if I discuss it, let f be a continuous function on the interval I. If we define the closed interval a and b, so we have to discuss some little bit idea about the closed interval and open interval. If it is a closed interval, that is a and b is included in this interval, and if it is an open interval like this, so we need not include a or x0 in between the interval. That is, we have to gather some concept on interior point and exterior point, whatever. Now I discuss again, let f is a continuous function on the interval ab, which is a closed interval, and x0 be an interior point of I. Assume that f is differentiable on a x0 and x0b. Then if the derivative, that is first order derivative, f x changes sign from plus to minus when passing through the point x0 from right to left, then x0 is a strict maximum point. This is a theoretical and graphical concept. If we define in our analytical manner, that in other word, in this case there exists a number delta greater than 0 such that for all x belongs to x0 minus delta to x0 implies first order derivative is greater than equal to 0, and for all x belongs to x0 and x0 plus delta first order derivative is less than equal to 0. And in language we must say that first order derivative changes sign from plus to minus when processed to the point x0 from right to left. How it is, I am depicting it through the graph. That is, here if we move right to left and the first order derivative is from negative, and then here 0 and here is positive, so this is a point of local maximum. That is, we have discussed it on here. Now similarly, if we say that the first order derivative changes its sign from negative to positive, then what it should be? It should be the local minimum. And if we discuss it through theory and analytical method, that is, let f is a continuous function on the interval I AB and x0 be an interior point of I, assume that f is differentiable on a x0 open interval and x0 be open interval. Then if the derivative, that is first order derivative, changes sign from minus to plus when passing through the point 0 from left to right, here we are moving from left to right, then x0 is a strict minimum point or relative minimum point or local minimum point. In other words, in this case there exists a number delta greater than 0 such that for all x belongs to x minus delta to x0, that is first order derivative less than or equals to 0, and for all x belongs to x0 and x0 plus delta implies first order derivative greater than or equal to 0. This is all about first order derivative test for finding local extrema points. Now we have to use some higher order derivative test for finding maxima minima, that is extrema, or there are some other definitions like saddle point, point of inflection. Okay, now the first criteria is first order derivative equals to 0. Then only we may conclude the point of extrema. And now if the second order derivative d2y by dx2 is also 0, then it is a saddle point or point of inflection. Otherwise, if the second order derivative d2y dx2 less than 0, then we will say that this point is a maximum and the curve is concave downwards. Now if the second order derivative d2y dx2 greater than 0, now we may say that the point is minimum, concave upwards. This is all about second order derivative test. Now if we depict it on a graphical manner, that if for this curve this is a inflection point, that is a saddle point, and this curve is concave downward and this portion is concave upward. Similarly, if this curve is considered, then this is concave upward, this is point of inflection, and this is concave downward. An inflection point is here for this curve, concave upward is this portion and concave downward this portion. We may depict the point of inflection like that. This is a tangent, this is a function moving curve, and this is a point of inflection. Now the base of finding all higher order derivative test to guess the optimum. I am saying that guess because in in-depth analysis of optimization theory, that some problem will converge or it may not converge at all, but the Taylor series expansion is a very concrete theorem for creating the base of all optimization problem. Now let fx be continuous on the interval, this is a closed interval AB, and first order two nth order derivatives of the function, said function f, are continuous. Now what is this? First order derivative to nth order derivatives of f are continuous, and n plus 1 derivative of f exists on the open interval AB. Then if x0 belongs to I, that is if x0 belongs to the closed interval AB, then for any x in I there exists a point xi between x and x0 such that if we would like to say the function polynomial is Pn equals to f of the first point x0, then the first order derivative of x0 into x minus x0 by 1 factorial plus second order derivative of x0 into x minus x0 whole square by 2 factorial, and like this the nth term is fn x0 into x minus x0 whole to the power n by n factorial, and we have told that the n plus 1 derivative exists, so f n plus 1 xi and x minus x0 whole to the power n plus 1 by n plus 1 factorial, and this term is particular called as Lagrange form of remainder. This is the highest order term, and this is called the Lagrange form of remainder. This expansion is called Taylor series expansion, and from this expansion we may derive the extremum value for any polynomial curve, etc. Now how to find n plus order derivative test? It may quite happen that the second order derivative is also not sufficient for finding minimum or maximum. First order derivative is a necessary condition, then after that the highest order derivatives are not sufficient for telling that the minimum and maximum value. Otherwise some particular conditions, particular criteria will be tested. Now here the first order derivative of a point C equals to the second order derivative, and up to nth order derivative equals to 0. In my previous examples we have seen that the nth order derivative is non-zero, then we are concluding that minimum or maximum. But if it happened that first order derivative to nth order derivative all are 0 and n plus 1 derivative is non-zero, then how do we conclude about minimum and maximum? Now see, if n is odd, then the f n plus 1 derivative of c is less than 0, then we must say that we would like to say that the local maximum exists at c. If n plus 1 derivative of c greater than 0, then local minimum at c. If n is odd, and we are categorizing it to broad two parts, and for each part we are calculating the n plus 1 derivative is less than 0 or greater than 0. If n is odd, then n plus 1 derivative is less than 0, then it is local maximum, and if it is greater than 0, then it is local minimum. Now what happens if n is even? If n is even and if n plus 1 derivative is less than 0, then we would like to say that c is a strictly decreasing point of inflection. If n is even and n plus 1 derivative of c is greater than or equal to 0, then we may say that c is strictly increasing point of inflection. Now I would like to discuss the other parts on later series, and so on. We will continue our lecture on the optimization theory. Fine, there are some good books for reference and further reading, and we would like to acknowledge all of these books and the personals involved for the optimization. Thank you. I am Supratim Chakraborty. If it is helpful to you, then like, subscribe and share. Thank you.